Unit Operation Classroom, GATE 2023, question 33. I'm Shekhar Bhattacharjee. The viscosity of an incompressible Newtonian fluid is measured using a capillary tube. And these dimensions are given. The diameter of this capillary tube is 0.5 mm and the length is 1.5 meter. The fluid flow is laminar, steady, and fully developed. So these are all hinting towards one equation, which we all know is Hagen-Poiseuille's equations. Flow rate is given, and the pressure drop across the length of the tube. So let's say these are two pressure measuring points, pressure being measured with a differential pressure transmitter, and this is 1 megapascal. All right. Um, so we have to find the viscosity. Normally we put that as mu, but they are putting as K. That's all right. Okay. Uh, so this is a very standard equation which is found everywhere in any textbook. So if we substitute the values here, so these are all the values, the value of mu, or which is equal to K, comes out as this one. So this value is going to be equal to 1.02. All the detailed calculations are shown in the website here. So as you know, this is a standard value for water, for any light hydrocarbons, also from light solvents. So this is a very, and this is a capillary. So normally, if that's a capillary, we can assume that to be laminar flow, since the diameter is very small. So this is a very easy problem, and main thing is that you have to use this equation. You have to recognize that we have to use this equation. But for that, we have to ensure that these conditions are satisfied, because these are the essential conditions for using Hagen-Poiseuille's equation. So if you want, you can stop the video right here. But if there is some more interesting information are given later on. So if you want to see those, you can continue watching the video. The first one we want to see, if the additional information, uh, we can calculate the Reynolds number just to make sure that this Hagen-Poiseuille equation is a valid one. So this is a standard Reynolds number equation. And this is my, of course, diameter in meter. This is the flow rate Q, and so these are just the area. So because this is we are putting this for velocity here, so we know this velocity is going to be equal to Q by A, which for a circular tube would be Q divided by pi d square over 4. That's what this one is here. So that's for velocity, and it comes around 5.09 meter per second. Anyway, so this is the density, and this is the viscosity which we have just calculated. And as you can see, the Reynolds number comes around 2495, so slightly above 2300. It's right in the laminar transition region. That's okay. So we can say that we can safely assume that Hagen-Poiseuille's equation is valid. Okay. Also, I just wanted to show you what are the different forms of Hagen-Poiseuille's equation you might see in different textbooks. Of course, one of the basic assumptions of Hagen-Poiseuille's equation is has to be for laminar flow of a Newtonian fluid, incompressible, just mainly the liquids, steady flow, fully developed flow, no entrance and exit effects in a circular tube. These are all important preconditions for satisfaction of Hagen-Poiseuille's equation. Okay, uh, so this is the flow rate form, which is very standard. This is in terms of diameter. This is in terms of the radius, which you have just seen above. So this is very standard equation. Another one you can see is the average velocity form, which of course here instead of Q, we can just write in terms of the velocity. And so this becomes in terms of the velocity, Hagen-Poiseuille's equation. And if you just take the delta P here, so that's the equation, the same equation here. Then there's a Darcy-Weisbach equation. This comes with from the very standard definition in terms of the friction factor, and we know this the Darcy's friction factor. Also, we know that the Darcy's friction factor is 4 times the Fanning's friction factor. We all know that. Um, so if we substitute this here, we basically get the same equation. It's just a different language we are using. Then, if you want to see the wall shear stress, you might see that this equation is also given in almost all the textbooks. So this is from the momentum balance equation. We get the shear stress at the wall, and once we put the value of delta P from the previous equation, which we have shown, you get this equation right here. Okay, so just an example, if with the same problem, if you want to calculate the shear stress at the wall, that's what the shear stress at the wall is. Okay. There is one more. There's a head loss form. We know head loss is defined into the pressure drop as this one. That's the relationship between head loss and the pressure drop. Okay. So if you take this equation and write in terms of head loss, that's what this equation is. So it's the same Hagen-Poiseuille's equation if you write in terms of head loss. Okay. And this is a very standard thing. The laminar velocity profile, we all know it's parabolic, and the maximum velocity is 2 times the average velocity. We also know that, right? Uh, is given in its standard textbook. So I just wanted to summarize all these things. What are the engineering applications of measurement of mu for the QC of the raw materials if they are of the right quality? Measurement of viscosity is one of them. Tracking the progress of polymerization reactors, the formulation of like coatings and inks and adhesive industry. So with that, let's go back to the original problem here, which we have discussed. And we just say that here, this value is equal to, we have seen, this is the answer. So K has to be equal to 1.02. That's the answer.